Thanks a lot for having me here, and thanks, Ke, for the introduction. Also, thanks, Stan, to organize this platform, and also for scheduling this talk. Today, I would like to talk about some deep learning work, what we already done. So the work are joint work with my talent colleagues. In my talk, I would like to cover both static MRI reconstruction and dynamic MRI reconstruction. In the next, I would like also cover we some cardiac MRI analysis of workflow using deep learning. In the last part of my talk, I would like to cover one application we using deep learning for solving interventional imaging application. MRI machine actually try to collect the data to fill in case space, right? If we have a fully sampled case space, we could directly apply inverse Fourier transform, right? Like the example I showed here, and we can get a very good image quality once we have the fully sampled case space data. But this procedure, MRI acquisition procedure, is pretty slow. That's because of some physics limitation, right? Patients have to stay in the country for a long while, and they feel discomfort in the country. Sometimes we found the motion artifacts in the image. That's because of the patient motion or the organ motion. And in order to speed up the acquisition procedure, right? I mean, in this field, we usually do the undersample the case space. That means during the acquisition procedure, we only collect the fewer case space measurements in the case space. On the right side, I'll give two examples. There are two different sampling patterns. And if we directly apply inverse Fourier transform, you can see from those images, right? The image quality is bad. That's because I mean the undersampled data violate the Nyquist-Shannon theorem, and we have the aliasing artifacts in the image. In order to reduce the artifacts and recover the image with a high fidelity, we have to use our algorithm, right, the reconstruction algorithm to recover the image from the undersampled case space. Traditionally, we could utilize the comparison sensing algorithm to do the optimization, and we recover the data. And in recent years, there are many deep learning work involved in this field to solve MRI reconstruction problem. Let's recall the MRI reconstruction from the undersampled case space data. Actually, it is a U-post inverse problem. In order to recover the data, we could utilize the optimization, right? If we for the U-post problem, we have to put the image regulator to those and reconstruct the image. If the regulator R here is differentiable, we could utilize the gradient descent optimizer to, eventually we get the recovered image. If we look at this part, right, if in this gradient descent update rule, we could utilize a neural network to predict this delta change in one gradient descent update. And the gradient descent update rule can be learned through either recurrent neural network or neural ODE. In my talk, I will cover these two directions. We utilize the convolutional neural network, and we all know convolutional neural network itself introduced the inductive bias, and those can be interpreted as a prior for inverse problem. We propose a pyramid convolutional recurrent neural network for MR reconstruction. Basically, the input of our neural network is the multi-coiled undersampled case space. Since in the reality, the scanner always acquire multi-coiled case space data. The output of the neural network is just one image with multi-channel. We have the real part and we have an imaginary part. Like I said, we use a recurrent neural network to mimic the gradient descent update rule. And we found the optimization problem, actually, if we decompose into several sub-problem, reconstruct the image from the chaos to the fine scale, we could reduce the searching space for the optimization. Specifically, we recover the image from the case space at a different scale. First, we recover the image from the lower scale and then the middle scale until we recover the image from the original the original resolution. And then finally, we combine this result for the final recovered image. In this way, the problem becomes easier. The network can easily find a good solution. Let's note that each sub-problem is solved through the convolutional recurrent neural network. Here, we show some intermediate result from the different scale, RN1, RN2, RN3, as well as the final combined result. We can see our proposed method could recover the image from the different scale, chaos to find details. And also from the ablation study, we observe if we use the multi-scale resolution in this way, we could generate a better recovered result than the individual scales in terms of PSNR and ISM. Our solution is one of the winner in the FASTA MRI challenge organized by Facebook 2019. Afterwards, we extended our method, and we also validate our method in both FASTA MRI knee data and FASTA MRI brain data. We also compared our method to state-of-the-art reconstruction methods. Our proposed PCRN outperform all those compared methods. Regarding the area map, we can also observe that our PCRN could recover more details than the compared methods. In the next, I would like to cover how we use a neural ODE to solve MRI reconstruction problem. I already explained, we could utilize the gradient descent to solve the inverse problem for this MRI reconstruction. If we reformulate the gradient descent into the following formula, the left side of the formula represent two image difference between reconstructed image in two adjacent reconstruction updates. And on the right side, this is a function. And we could use a neural network to represent. I already explained we use a neural network, a recurrent neural network to represent this update rule. But this is the discrete optimization procedure. If we think about, this optimization as a continuous flow problem, we could transform those gradient descent optimizer into a ODE problem. And we can evaluate, the ODE through the, we could, treat the MRI reconstruction as evaluating the ODE problem. Given undersampled image at T0 and given the dynamics F, reconstructed image can be predicted through evaluating the ODE. Here, if we represent the dynamics F using the neural network, then this problem become a neural ODE problem. And we could either using fixed off-the-shelf ODE solver to solve the neural ODE, or we could use a learned solver to solve this problem. For the off-the-shelf solver, we could either use a very basic Euler solver, or we could use RK solver, such as RK2 and RK4. Those basic off-the-shelf solvers are discovered and discussed, in the original neural ODE paper. And they utilize either the learning the ODE through the backpropagation or the ODE solver, or they could use the joint method. And here we have to set up a couple of the hyperparameters. Instead of setting those hyperparameters, in this work, in this reconstruction, medical image reconstruction work, we proposed, we utilized the neural network to learn those solvers. Basically, we propose a different network structure just to mimic the behavior of those solvers. We come up with the learned Euler solvers, and we come up with learned RK2 solvers and the RK4 solvers. I want to go to details to explain the exactly network structure. If you are interested, you can refer to our paper. We evaluate those off-the-shelf solvers with the different learning strategies and also the learned solvers. And we also compare the three methods on the first MRI data set. Based on our experiment, we found those ODE-based methods use just a few network parameters. We could recover good image quality and generate a very comparable reconstructed result to those compared methods. We also extend our neural ODE network for MRI reconstruction problem to another optimization problem. This is the image resolution problem. If we recall that, image resolution can also be formulated as a optimization problem. During the optimization, we try to either figure out the deformable field parameters or the affine transform parameters. We could also utilize the gradient descent if we formulate the problem properly. And this gradient descent problem can be solved by the neural ODE, very similar to our image reconstruction problem. But we found the image resolution problem requires an extensive number of function evaluation by ODE solver. To resolve this problem, we come up with a multi-scale ODE network. Basically, we divide the time interval into the three parts. For each part, we do the neural ODE evaluation onto the different scale of the image. The first scale, we do the neural ODE evaluation for the lower resolution, and then the middle resolution, and until we finish the evaluation on the original image resolution. By this way, we solve the neural ODE at a different resolution, and the time cost for function evaluation is much smaller. The searching space for image resolution is largely reduced. We propose this multi-scale ODE neural network to solve the image resolution problem, specifically for the multimodality image resolution. I won't go to the details for the evaluation. If you are interested, you can refer to our paper. In the next parts, I will talk two major topics. One is for the cardiac MRI medical MRI reconstruction. The other one is for we use deep learning to solve cardiac MRI data analysis. Basically, for the cardiac MRI, it includes many sequences. It contains cardiac Cine data, T1 map, T2 map, T1 weighted, T2 weighted, perfusion, RGE, or flow data like 2D flow or 4D flow, and so on and so forth. But today in my talk, I only cover Cine cardiac MRI. Basically, for the Cine data, they are the video data. When we acquire those data, actually, I mean, the acquisition in this cardiac MRI are 2D acquisition. I mean, we acquire the data from the different direction. Basically, what we collect, we have the short axis data. For the short axis data, we cover the entire heart. We cover in average from in average 9 to 12 slices. And for long axis, we cover at least one two-chamber view, one three-chamber view, and one four-chamber view. On the right side, those are examples to explain what the short axis data looks like and what the long axis look like. Basically, we cover the heart, I mean, from the different angles. Cine cardiac MRI is the clinical standard for cardiac functional analysis, but there are two major pain points in the clinical application. One is the acquisition. The acquisition itself is pretty slow. The patients stay in country for a long time. Especially they have to hold the breath for quite a long time and several times in order to get rid of the motion artifacts. And since those data are video data, ECG signal are also utilized to gate the acquisition. In next slides, I will talk about more details about those acquisition problem. Once we got the data, we have multiple slices and have lots of video frames. So in reality, we have the we have the fully manual tools or semi-auto tools for analysis. But actually, there are still tedious work the cardiologists or radiologists how to perform. So the fully automated tool is required. I will cover our solution, how we use deep learning to solve cardiac MRI analysis workflow problem. Basically, in the clinical acquisition, we acquire the Cine data retrospectively. That's why we call Cine usually as a retro Cine. The patient, like I mentioned, how to hold the breath for several times during the data acquisition, and the ECG signal is utilized. So why we need the ECG signal, right? There are, since the acquisition is slow, in order to fill in the case-based data for just one time point, actually we need to collect the data from different cardiac cycle. If you look at the illustration at the left bottom, I show the ECG waveform for just one slice at one time point. I mean, as the first cardiac cycle, we fill in a few case-based line. As the second cardiac cycle, we fill more case-based line. And the third one, we fill more until we fill entire case-based data. And then we can utilize the Fourier transform to recover the data. And we repeat this procedure for every slice. And for each slice, the patient have to hold the breath, and the ECG are utilized to get this procedure. Can we speed up this procedure? That's for sure. I mean, we come up with a real-time Cine imaging sequence. Basically, just ask the patient to hold breath once, just from 12 to 15 seconds. And that's it. We got all the acquisition for entire heart for the all the cardiac phase we needed. We utilize a variable Latin hyper cube undersampling pattern that's designed by our UIH colleagues. They have this work 2019. We utilize this method to generate the sampling pattern, and at each time point, like the figure show on the right bottom side, at each time point, we fill in all the information what we need. And then for the second frame, we fill some other case space, some other based on some other pattern, we fill in the data required for the second phase, and so on and so forth. And we can gather all the data. I mean, for just one cardiac cycle. For second cardiac cycle, we just acquire another slice. In this way, we could reach close to real-time acquisition, but this high accelerate rate will pose a challenge for MRI reconstruction. We extend our recurrent neural network reconstruction method from static MR reconstruction to a dynamic MR reconstruction. We utilize a bidirectional RNN. Actually, this bidirectional method first proposed by Qin in 2018 in their TMI paper. We extended their work and utilize bidirectional RNN to capture the temporal information during the MRI reconstruction. If you look at those results on the left bottom side, the first one, actually this is a direct, we directly apply a inverse Fourier transform. Actually, we are not able to see the structure from those reconstruction, but if we apply the AI, we could easily recover the results from those aliasing artifact impact data. We deployed the sequence and the reconstruction algorithm into our MR scanner. We acquired the real data. On the right side, I just gave you a couple of examples generated from our method on the UIH scanner. And I have to highlight the second video on the top. This video, if you take a look at this video, and the patient actually during the acquisition, he or she is not able to hold the breath, but basically we still can recover the image with high image quality. And another highlighted video we can take a look at is the last video on the right bottom part. This is actually on the basal part of the heart. You can see the mitral wall. This region is between the left ventricle and the left atrium. Actually, the blood flow from the left atrium and into the left ventricle. And you can the motion is very severe, but we can recover. Even we do not have the ECG signal, we can recover the data very well. When we evaluate the reconstructed image, we not only utilize the traditional metrics such as the PSNR or SSM. Actually, since the Cine data is the clinical standard for the functional analysis evaluation, what we adopt here, we utilize a downstream task to evaluate the reconstructed images. We collected in total 216 CMR data from 7 volunteers and 1 more patient with cardiomegaly. And for each subject, we acquired basically 3 data sets with different protocols, with different reconstruction method. One is Retrospective Cine. This is the clinical wide accepted protocol. And one is CS Cine. And the other one is a deep learning based method, what we used. I mean, I have to say here, CS and DR Cine, the sequence is exactly the same, but the reconstruction algorithm is different. For CS1, we directly use a comparison sensing method. We perform the cardiac functional analysis on those reconstructed data. And the fully automated functional analysis software developed by us is utilized to evaluate those data. Here, I only include the ejection fraction in my talk. From the ejection fraction, I mean, on the left side, the bar chart indicate there's no, statistically speaking, there's no significant difference between the deep learning based method and Retrospective. And from the right side, this is the Bland Altman plots. We can see our method for either left ventricle or right ventricle. Our method generate a consistent result to the Retrospective. In the future, we would like to expand our evaluation on a larger population. On top of the functional analysis, with those metrics I talked about, such as end of diastole volume and systole volume, ejection fraction, myocardium mass, and so on and so forth. I mean, in recent years, actually the myocardium strain become pretty popular. Myocardium strain actually it's used to measure the myocardium deformation from the different direction. Like, and it has been shown to be an early indicator for the cardiac dysfunction. It is even much earlier than the ejection fraction has changed. Since for CMR, all the acquisition is 2D. Such as we have the short axis data, we have the long axis data. All those, I mean, video data are acquired in 2D form. So for myocardium analysis, usually we decompose the strain into 3 directions, from longitudinal strain, radial strain, and the circumferential strain. We come up with a fully automated solution using deep learning. I mean, for several components in the entire analysis workflow. First, once we get the DICOM data, we use deep learning to do the view classification. We let the machine knows which video is short axis, which video are a 2-chamber view, long axis, or 3-chamber view or 4-chamber view, long axis views. And then we send it into the next components. First one is the landmark detection. We use our neural network to detect the key landmarks on the short axis to identify the insertion points between the left ventricle and the right ventricle, and also some key points like the basal points and apical points on the long axis views. Based on those landmarks, either we can define the heart region for further analysis, or we can define AHA 17 segments. Since in this domain, cardiologists or radiologists are quite familiar with or get used to those 17 segment analysis, since those AHA 17 segments are highly correlated to the coronary artery branches. In the next step, we use deep learning, we use the neural network, we do the segmentation, we segment short axis and the long axis view. We got the myocardium segmentation, the peptide muscle segmentation, left ventricle, the blood pool, and right ventricle, and so on and so forth. And based on the segmentation, actually, those segmentation, what we do, we perform the entire heart and also cover all the frame. Based on the segmentation result, we could derive the functional analysis, and we could represent the left ventricle, right ventricle volume using the volume curve, or we can represent just use the 17 segments. I want to, in my talk, I want to go to detail for the segmentation task, but later I will explain how we use deep learning to solve the motion estimation. In the next component, it is a motion estimation based on the motion. Once we have the motion field, we could derive the motion, the cardiac motion, and we based on that, we derive the string analysis indices and represent those indices. Either use the curve to have the global representation or the segmental recommendation, or we could use utilize the 17 AHA. The plot chart to represent the results. In the next, I will explain how we use deep learning to solve the motion analysis problem. We come up with the motion pyramid network, and also we utilize the transfer learning to improve the performance. Basically, our network estimate the motion field from the different scales, and then we combine those scales as the last neural network layer, and then we get the more accurate result. In order to improve the motion estimation for the large motion, we come up with a progressive motion composition strategy. Basically, it is a step-by-step based method. We need several steps. We just repeat the neural network into several steps and recover the motion estimated field in more accurate way. But we found it will take some time. In order to reduce the time, we utilize another neural network. We clone exactly the same width from the backbone of the teacher network, and then we use a fine-tuning based method. We distill the teacher's knowledge to the student. Use this teacher-student training strategy to make the student gain the capability of the teacher. In this way, we get a more accurate motion estimation in a faster way. It is well known that medical image, especially for the MR data, we face the domain shift problem. So where does the domain mismatch come from? Actually, they can come from the different MRI acquisition protocol. Different operator could set up different parameters for optimizing the acquisition, and the domain shift issue can come from the different type of scanner, such as 1.5T or 3T scanners. And the scanners can come from the different vendors, and the vendors utilize their own reconstruction algorithm. The algorithm can be very different, and we could utilize either fully some of the data or the parallel imaging, or the CS-based method or deep learning-based method. Once we found those mismatch, right? We found we will see the performance drop in the delivered data. In our problem, we try to address this issue for motion estimation problem. But actually, for the motion estimation, it is a self-supervised method. It's similar to the image visualization, right? Basically, if we have a network already trained offline, we can deploy this network onto the real data for one single video, and we run the network, we generate the result. Basically, from those data, we can fine-tune the neural network to try to overfit the width to this data site. And then if we can overfit to just one single data for this data, we can get, a good performance. And we repeat this procedure for the different, videos. But this, online, since we already deployed into the, into those video, right? The speed is we have to consider. The fine tuning is slow. How can I improve this? Improve the speed? We come up with a meta-learning based method. It is similar to the MIMO, but what we saw is we utilize a meta-learner. And we train the online learner offline. Just to mimic the offline, not offline, the online model adaptation. We use the meta learner to train this online learner to try to let the online learner to gain the capability to adapt with to certain video. In this way, we could improve the speed. We observe just within 3 to 5 iteration, we could update the width and adapt the width to certain video in a more accurate way. Based on our method, on both inside the distribution test site and also the outside the distribution test site, we significantly improve our method to compare to the baseline method. Here we show some result, the tracking result for long axis and short axis. On the top, those are feature point tracking for the long axis view. Here we can see the tracked points for myocardium region for both outer boundary points and inner boundary points. All those points, inner and outer, correlate each other, and through the frame, all those points are corresponding each other. So with those correspondence, actually, we could derive the string. The string is utilized to analyzing the deformation. And the bottom row, we show the first one, we show the short axis feature point tracking. And the last 2 video, we show the dense, the radial string, and the circumferential string for short axis. All those strings are derived from the dense motion estimation field. We evaluate our deep learning-based string analysis pipeline to one existing method. It's called a MyoString. Basically, MyoString utilize another additional acquisition. It's called FastSync. They have to implement in the scanner and do additional acquisition. And the MyoString just provide 2 string analysis. One is a longitudinal, one is a circumferential. And this company called myocardium solution provide the MyoString solution it can derive the string numbers from the this fast sync based acquisition. Our deep learning based method does not need additional acquisition. We directly utilize the Cine. I mean, our solution could provide a longitudinal, radial, and circumferential string from these three directions. In our experiment, we include 9 cardio-oncology patients and 11 patients with no cancer therapy. And based on the results, we observe that our fully automated solution correlated very well with the fast sync based method for the circumferential string, but there is a systematic bias we found in the longitudinal string. And we know this bias can occur just because sync-based method calculate a through-plane string, but our deep learning-based method, since we use the Cine data, the Cine, based method calculated the in-plane string. And we found from the previous publication in the previous studies, we found there are some shown systematic bias too for longitudinal string for those feature tracking based method. Feature tracking, that means that they use Cine data to derive the feature tracking based string to those fast sync based method. In the last part of my talk, I would like to cover just one application. We solved the interventional imaging. On the left upper corner, I show this CMR machine. Usually in the surgical room, the surgeon, the physician, utilizes those machines to acquire the real-time X-ray videos. The surgeon utilizes those videos to guide their interventional, minimum interventional procedure. On the right side, I put just one example and this is a fluoroscopy video for PCI surgery. We can see from the video, we can observe the catheter, the wire, and the other device like the balloon marker, the balloon, and so on and so forth. And during a couple of frames, the physician injected the contrast. We can see the coronary artery after the physician injected the contrast. Once the blood flow wash out the contrast, we are not able to see any coronary artery in the image. Basically, for the PCI surgery, the physician need to first deploy the catheter into the coronary artery, and also place the wire into the certain coronary branch. And they utilize those devices to try to deploy the stent into the stenosis region. Stenosis is a narrow part of the coronary artery. Once they finish the deployment, they use a balloon to try to expand the stent. Once they done this procedure, they will pull back all those devices, such as the catheter, the guide wire, and the balloon markers, all those devices, and leave the stent in the coronary artery and make sure the blood can flow through the vessel as usual. Before they pull back those devices, the physician need to check the stent status, whether the balloon is already deployed in a correct location, and whether the balloon is dilated, whether the stent is placed in a correct location, whether the stent is already expanded sufficiently, whether during the procedure the stent is broken, is there any fracture in the stent, whether they need to place another stent. So you need to check those status. But actually in the real data, the surgeon with the patient in the surgical room, right? They very care about the X-ray dose. I mean, they always, during the procedure, they always keep the X-ray on, right? When they want to see, the organ inside the body, they usually use a low dose. If they use the low dose, the image quality is poor, and they are not able to see clear stent visibility. And we can observe the motion from the stent. So the motion caused by the both cardiac and the breathing motion. The one solution to improve the stent visibility, we could remove the cardiac and the breathing motion, and then also enhance the SNR on the stent region. What we do, actually, we know there are key points. The surgeon deployed inside the stent. There are two small key points. We call the blue markers. If we could robustly detect those markers through the entire video, frame by frame, and then we align those marker locations, we could, remove the stent motion. And if we overlay all those, align the image together, and we can get just one image. Since the motion is removed for the stent, we could get a very good stent visibility with high SNR. And the background, we can blur those background. The marker actually in the image is pretty small. Usually the image resolution is 1K by 1K, but the marker only contain a couple of pixels. And in the image, we can observe some other, actually a lot, some other small marker dot like a structure. And the X-ray is a transparent modality, and we can also see the marker is overlaid with other device like the balloon, like the stent, like the other catheter or the wire across the stent. And those markers can be overlaid with the other organ, such as the lung, the diaphragm, the heart shadow, or the bone, like the rib. And robust detection is quite challenging. What we do a tracking-based method. We come up with an end-to-end solution. In our solution, in the first step, we use a unit-like structure. We do a landmark regression first. We regress the landmark locations. Certainly, we get the heat map. And in the heat map, we have the detected landmarks. But those landmarks, we have the true positive, we have the false positives. In the next step, we need to reduce. We need to remove all the false positives and keep the true positive. In order to doing so, we form the pair for a stent, and we get a bounding box based on this formation, and send those bounding box as the object proposal into the next step. We have a resonate, and for resonate, we extract the feature from the frame, and for the bounding box, for each bounding box, we get the feature from different level of the resonate, and we do the average pooling, and we get the feature for the stent proposal. And then in the next step, we utilize a graph convolutional neural network, and we do the stent tracking, and we try to identify the real stent by temporally reasoning method. Basically, we establish the graph first. The graph node represent the stent proposal. We build the graph node for each frame, and between two frames, for each stent, we connect using the graph edge. The graph node, the initial feature we set up based on those resonant feature, and for edge feature, the initial feature we set up either based on the image feature or the geometry constraint feature, and then we send the graph into the convolutional this a graph convolutional neural network. We use the GCN to update the node feature and the edge feature. And eventually, we have the last layer. And for the last layer, we collect those nodes and with the feature, and we do the node classification. And then we know which one is the true positive and which one is false positive. And we have another additional step. We use the detection result to correct the hidden map. In this way, we can complete end-to-end training. We evaluate our method on both in-house data set and external data set. For the in-house data set, this is a PCI-based data set. We compared our method to a coordinate regression-based method and center net-based method with different network backbones. We found our method is significantly outperform those compared methods. For the external data set, it is a TAVI data set. Basically, TAVI is different as the PCI, but we figure out one, landmark constellation is very similar to the PCI. So that's why we utilize those constellation for the evaluation. We train our neural network on the TAVI data and also evaluate on the tested data set. We observe our tracking-based method certainly is better than the compared method. Here, I gave some example, the tracking example with in the videos. From the video, we can see landmark tracking result. Those small white circle, just the circle the landmark. We can robustly track the small landmarks. And beside those videos, I just put the downstream task result. Those are standard enhancement result derived from the landmark detection tracking results. We can see much clear stand visualization compared to the video results. You may ask one question that maybe the surgeon can, stop the video and take a look at just one single image, right? Since a single image, there is no motion. I put some comparison here. If you look at the single frame from the image, if you can follow my cursor, right? We are not able to, from the single image, we can not able to see clear stent structure, but if you look at the stent enhancement, we can see those mesh structure for the stent, very clear. The surgeon and the physician can utilize those visibility to make their clinical decision. This is another example. I have to highlight this region in original image, right? If you observe this region, we are not able to see anything, almost anything. Yeah, but on this side, we can see very clear, stent structure. Today, I already talk about this 4 topics. One is static MRI reconstruction, we formulate as a recurrent neural network and a neural ODE problem for MRI reconstruction. We extended this method for cardiac MRI data acquisition. I mean, based on our method, we minimize the patient's breath holding and also remove the ECG signal and make the cine acquisition more applicable in practice. We also propose a fully automated solution using different deep learning components for myocardium strain analysis. In the final part, I talk about a combination of CN and GCN based method for stent tracking. This solution actually provides a good opportunity for enhancing the stent visibility. We hope this method in the future could help the surgeon to complete their PCI surgery. I have to thank our previous talent students, and they made a great contribution to those projects I already talked about. I also appreciate a good collaboration from my colleagues from UII, also from UIH, also from external collaborators. Thank you. I think that's all from my side. Any question?
Thank you. Very impressive works. So we have currently we have 5 questions in the QA session. The first question is, what is the evaluation measure for MR reconstruction task? Oh, sorry, that's the second question.
What is the evaluation measure for MR? Okay, I mean, we separate into two parts, right? I mean, the first, for static one, what we evaluate just based on the very traditional method. We use the PSNR and ISM, those metric, quantitatively to evaluate our reconstructed method and compared to the fully sampled data. We treated the fully sampled data as the ground truth. And another method what we utilized, we directly deploy our model into the machine, and we acquire the real data from the machine. For this time, we do not have the ground truth, but we can acquire separately the fully sampled data. We send those data to the radiologist. They can, I mean, visually check those data, and then they can give us some quality scores. The third method in my talk I already covered for the dynamic MR reconstruction. I already covered for this cine data acquisition. What we do, we acquired our deep learning based method, and also the clinical widely accepted method, those two methods, and we acquired the pair data separately, and we use a downstream task. Downstream task, for example, we use the functional analysis. We get the functional analysis parameters, and based on that, we try to found some correlation, whether our reconstructed method correlated well to those clinical widely accepted method. I think that's 3 major, evaluation what we done in our work for MRI reconstruction evaluation.
Thank you. And the next question is, are the coil channels combined, or are they separately fed into the network?
And basically, for the coils, right? We first we have a coil compression layer for different size of the coil. I mean, usually in the clinical, so we have a different number of the coils, right? We first do the coil compression. We usually reduce it to 12 to 16 coils. Since then, we standardize the number of the coils, and then we treat the coil as the multi-channel data. And then we send it to the network, and we do the reconstruction. In our method, we did not do the coil compression. We found actually in our paper, TMI paper, we compared, multi-channel based method usually generate a better result than the coil compression, than the coil combination.
Thank you. Next question. Has the inverse FFT in the reconstruction process been changed by the deep neural network?
So inverse, actually, we treated the inverse FFT just, there are two parts for the reconstruction. I haven't covered the detail, right? The one part is the data consistency. And once we recover the image and we do the Fourier transform, we convert the image into the K-space, and then we verify the case-based data to the measurement. Measurement is the original acquired case-based data. We also use the inverse Fourier transform to generate the initial result, right? When we do the image recovery, we're working on the image domain. Acquisition is on the case-based domain. Recovery is on the image domain. So that's why we utilize inverse Fourier transform to initialize the neural network reconstruction procedure. And step by step, we update this image to add some gain to the image, and we remove the artifacts from the initial inverse Fourier transform results. I don't know whether I already answered this question. Yeah.
Yeah, thank you. And also, someone asked, can you share the publication of these works?
Yes. For those publications, I already listed the paper right in my talk. I can also share the paper.
Yeah. So the next question is, how much training data do you need for the first two methods, MR reconstruction, to capture real-life variability?
For the first static MR reconstruction, since we utilize the public data, right? We use all the training data set in the first MRI training site and validate on the test data side. For the dynamic MRI reconstruction, we use hundreds, patients' data and volunteer data, and those hundreds actually contain, for our initial work, contains thousands of videos. Yeah, thousands of videos to do the MRI reconstruction. And we found, since the method we utilize here is based on the idea is we try to learn the capability, like the neural network, to learn the capability to learn how the network recovers the image from the case space and following the optimization rule. Right? Once we gain this capability, we found the generalization capability is very well in the real life time, and we already, since usually in this field, in MRI reconstruction field, when we prepare the training data set, when synthesize, right, we synthesize from the fully sampled case space data, and we train neural network. We use the fully sampled data as the ground truth, and when we deploy it, we directly generate those unsampled data from the machine. So it certainly has some gap between the machine directly generated sample and the training set. But we found our method works well on the real lifetime. Yeah.
Yeah, that's very important to for the method to generalize to real life applications. Next question is, what is the status of deep learning algorithms now in actual clinical practice, and what are the challenges you think deep learning has to face to become the dominant algorithm in clinical practice? It's a very general question.
Actually, in the, from deep learning, right, in this domain, we have two visions, right? The first one is, also in my talk, I already covered these two visions, right? The first one is how can we make the scanners much efficient, much more smarter. We certainly utilized deep learning to solve the denoising problem and also the reconstruction problem. And there, my understanding, right, not just for UIH and for Siemens, for GE, for Philips, there are many deep learning algorithms already deployed in the scanner and to serve this purpose, right? To make the image quality much better and make the scanner much efficient, much more efficient. And another challenge, is also our vision, right? Is how can we, once we get the data, how can we make the radiologist, cardiologist, or neurologist, and so on and so forth, all those physicians' life better. And we certainly can help them to improve their workflow, right? We not like we use deep learning to replace totally replace this their work, but can we improve their workflow and optimize some procedure? Certainly, deep learning not able to address the problem 100%, right? In this domain, we face the long tail problem. So if in the real deployment, if there's some problem, how can we remedy, come up with remedy, right? So in the real clinical environment, even the deep learning already deployed, right? We certainly can also provide some interventional tools, right, to let the user get involved in the circle with the machine learning, with the computer aided algorithm to complete their diagnostic job. Certainly, I believe, the domain shift and those data scarcity issue still is our major challenge for the clinical practice, right? And in my talk, I also gave another example, right? Deep learning not only to help the radiologist, we can also help the physician in the surgical room. We provide some additional information. What before deep learning, before machine learning, was the surgeon not able to acquire. We extend their capability to complete their surgery. Yeah.
Oh, so Dr. Sun, you mean the deep learning-based MR reconstruction algorithms have been deployed in real-life machines, is it?
Yes, in this year, RNCA, right? Many vendors already mentioned this, right? Even deep learning-based method, for some companies already get FDA, right? Yeah, I'm not talking. I have to note that the method I'm talking about is not a commercialized method. Yeah, but what I know, right, there are many methods already commercialized. Yeah.
I see. Yeah. So next question is, in your opinion, what would be the approach to reconstruct an isotropic MR from multiple anisotropic MR sequences?
Oh, actually, so then definitely, So for MRI reconstruction, usually most of the time MRI reconstruction is 2D, right? This is due to the limitation of MRI sequence. Certainly we do the 2D and 2D based on MRI reconstruction. For 3D MR reconstructions, what we do, we definitely we could do the isotropic data generation for the image domain. But if we do the image domain, we cannot cover the case space. Usually, actually, we can directly recover isotropic data. Or for the any isotropic data, if we utilize, let me think about it. If we utilize the method, what I'm talking about, right? If we utilize recover MR data for use deep learning for optimization problem, not just for the denoising problem, I believe it probably work. I mean, for the anisotropic data. But certainly the interpolation may not work just because if we do the interpolation in the case space, we are not able to easily to recover the case space from the image space. I haven't done this direction because most of the time we do the 2D 2D reconstruction.
I see. Next question. For motion tracking, what is the minimum number of images or training data size which is required? Does this estimate change if there is no closely related data set available to learn from using transfer learning?
Basically, for the motion-based method, we can easily get the data since we do not need ground truth. I mean, there is no ground truth basically. Yeah, what we do is just similar as the visualization problem, right? We formulate it as unsupervised machine learning, the self-supervised machine learning, and we compared the warped data to the fixed data, and then we apply the loss function, so we can collect lots of data. And for trading, I mean, a good learner, right? Definitely thousands of data is sufficient. That's what we observed, and we also observe, right? Like I mentioned, I mean, certainly we face the domain barrier problem between the training data and the test data. We can just do the fine tuning on the test data since we do not need a ground truth to train the neural network. For the fine tuning, what we utilize here, we use a meta learning based method. It's derived from MIMO. It can save the iteration of the fine tuning. It can be very fast. Yeah.
Thank you. Next question is, can we use the reconstruction method to improve the resolution in terms of number of slices? For example, from 3 slices to 30 slices.
Could you repeat this question?
Can we use the reconstruction method to improve the resolution in terms of number of slices? For example, from 3 to 30 slices.
Improve. I don't know. I'm gonna guess this question. What do you mean the number of the slices here? To generate more slices, right?
Yeah, maybe.
Oh, then I got it. So I mean, this is basically we can use deep learning to do the super resolution across the slice. So certainly we can try this. Use the super resolution.
Yeah. Okay. We have one last question. How do we know that the result of stent enhancement is right?
Oh, basically this is, I mean, the stent enhancement result is not synthesized based on deep learning. We just overlay all the images together. Just image processing problem. If there is information, if we do the overlay of all those images, I mean, if the stent is there, I mean, think about it. We have multiple images, and if we overlay and do the average, right, we can, I mean, reduce the noise, Gaussian noise, for example. We can make the foreground has a good SNR. This is basically our strategy. But what we do use deep learning here, we use the landmark detection to find where the stent it is, and then we remove the motion. When we remove the motion, right, all the stent motion is exactly the same, it becomes static, and all the background had a different motion. Before the background, maybe before we do this alignment, the background has a similar motion, right? But after we align the stent has the same motion, but the background has a different motion, and the stent can standing out in terms of visualization. It's just based on signal processing. It's not synthesized, so it's trustable. Yeah.
Thank you. Okay, so we have answered all the questions. Thank Dr. Spin again, and thank you everyone for joining our talk.
Yeah, thanks a lot for having me here. Thanks a lot for those questions.